Good afternoon, everybody. This is the second presentation today, part of the Trust's contribution to Wellington Heritage Week. My name's Nick Bevan. I'm the current chair of the Trust, who has the privilege of owning and caring for this building. And part of the ownership of this building is to make it available to people as often as we can, and also to use it as a hub, if you like, for presentations to do with art, architecture, music, anything to do with the arts and the science. And today we're actually going to have a bit of science because we have a structural engineer with us today, Alistair Cattanach, he's a director at Dunning Thornton Consultants. And Alistair is passionate about architecture, and he is a collaborator with many architects here in New Zealand. I say collaborator because I think Alistair's understanding of architecture and how to synthesise that with his structural genius is many architects are drawn to it. So much so that I think Alistair's got quite a workload in his office. So he's had structural engineering experience in the UK as well as in New Zealand, and he has particular skills in strategic planning and complex analysis, base isolation, and he's been involved in a lot of timber design, seismic assessment and heritage buildings. And I'm sure that Alistair will be talking to you about some of those projects, and I believe he may even be talking about this building at some point. So with the benefit of the support from LT McGuinness, who I think is also be a company that Alistair would be very familiar with, who have provided the financial support for this event and also enabled us to have it as a live streamed event as well as being recorded. It's my pleasure to welcome you, Alistair, to Futuna, and to come up and take the stage and provide us with your presentation. Welcome.
I think it's very interesting giving a second presentation for something that's so almost opposite to what Carolina does, because everything she does is so measured and careful and in the millimetres, probably centimetres because she's European, but it's all in the delicate detail, whereas us as structural engineers, we come in and we're measuring in tonnes and metres, and we're doing these massive things to these buildings. And I think there's been a lot of tension of that, and New Zealand's taken a while to mature, and we're still maturing in what to do with this. And so my talk, what I'm trying to do is ask a bunch of questions, talk about things we've done. They're not all things we'd want to do now, but it's sort of a philosophy, and the more conversations we have about this, I think we as engineers and the architects and the heritage architects who work on these projects will get better at doing what we do with more involvement from the public in these sort of decisions that happen behind the scenes. So I'm going to contrast some groups of buildings just to try and articulate the point that I'm making. So starting off with Shed 11 and 13, we got asked to look at the seismic strengthening of Shed 13 and by Ian Bowman. Shed 11 had been strengthened in the past, and so that was kind of the template of what to do. It's an 80s strengthening. We were still really much learning back then. And in the 80s, a new concrete frame was cut into the brick at the side of the building, and it was taken up to just below the trusses. And there were some sort of straps put on, but the building wasn't, what we found out, the building later was still earthquake prone. It had some problems at the height of where it was joined at the roof, which we've seen in Christchurch is very important. The connection between the walls and the roof is very important. It wasn't a very good project as a precedent, so we decided, okay, well, let's start again. And when we got to Shed 13, it's a pretty amazing building. It's very structural, it's very heavy. And what Ian said to me at the beginning, he said, like, you walk in, and this is the completed building before everybody moved in. You walk in and you look up at the roof, it's a bit like this building. And, excuse me. what we engineers tend to like to do is put frames in buildings. And my first reaction to this building was to put frames in the building. And then I thought about that and I reflected on what Ian had told me, which is that you come and you look up. And so if we're putting these new structures across, we're fighting about the direction. So the inspiration was to turn our thinking upside down. So instead of putting the frame up this way, we turned it up and did all the work in the foundations. And so we put large beams under the floor, and then we cantilevered these columns up, but we didn't put them in the brick. So we put them in separately. We made them out of press-dressed concrete, so that's concrete that's got wires that have been stretched and then let go, and so the concrete doesn't crack, it's very compressed, which makes it very stiff. So it was my way of trying to put a structure in it that was as close as I could get to mimicking the stiffness of the old brick walls. What we did to the brick walls was we post-tensioned them as well, so we cored holes all the way down into the foundations, and we put cables in which we grouted into the foundation and then stretched and clamped them down on top of the brick. And so what that does, it's like, I give the analogy of picking up dice off the table. If you push hard enough, you can pick them up. So we're doing that to the walls, we're squashing them. And that means that the bricks, when the earthquake loads try to bend the walls, the clamping stops them snapping through. So we ended up finding this way of tuning a system where the old walls were kind of rocking on the old foundations, they were clamped down, and we had these new stiff columns that we put these bits of steel on the top that would bend backwards and forwards in the earthquake. So these little bits of steel are only about this big. And so they absorb the earthquake energy, because when structures rock, and we see this with statues and stuff in earthquakes, there's no energy dissipation. They rock and then they fall over. So what we needed to do is absorb that earthquake energy, slow it down like the shock absorbers do on your car. It's not just springs, it's the shock absorbers too. So what we were trying to do is let the building rock like it wanted to, make it a bit stronger by post-tensioning it, and then absorb a bit of earthquake energy. So a lot of things going on technically, but I guess that where I think this project came very well together was using the Ecomos Principles, which is to make something what you do as a structural engineer transparent and reversible. So we were putting these new columns that weren't touching the existing. It was obvious what was old and new, and that, you know, if we find magic ways of strengthening these buildings in the future and decades to come or generations to come, that these could be removed from the building. So I'm not sure if things need to be removed, but it's the concept that they could be helps you as an engineer kind of pull them apart and make the legibility between the two items work. So. So to do that, what we had to do is go up to Otaki and make these very strong, stiff columns up in the precast concrete yard. So we were using kind of cheap commercial technologies, if you like, but you know, a nice finish on the concrete. Then in terms of hiding it, so we were showing it for the mullions, we then laced the top of the wall together with a steel truss. Now, because it's got very large cornices on the outside of the building, there was a gap between the cornice and the brick, so we were able to pass along bits of steel and angle and actually make a truss that capped off all the walls around the perimeter. This is a rough sketch I did in the design meeting trying to explain what I was trying to do. So you can see that in the building, just running along the tops of the brick walls, there's just a bit of a steel angle. So that's all laced up, and so that means that the columns join up all the way along the walls, and it means that we didn't have to do anything to the roof. All we did is we re-nailed all the timber boards down. We didn't put new structure on the roof because we wanted to leave it in the state that it was, and putting this angle in the right place. Finding that location was a really big part of it. So really, this is the kind of you can't actually get into this building, which is a bit disappointing because Mojo have it privately. But you can see where all of the interventions are spaced off the brickwork. It's very obvious what's new and what's old, and they're very different architectural gestures, if you like. So it's I think this is a particularly good job. Just so to reassure you, we then went back and addressed Shed 11 5 or 6 years later, I think, and so we've ended up post-tensioning all that brick down and trying to make the existing strengthening work a bit like what we did here at Shed 13. So we've managed to strengthen that building too, and it's got a sort of similar foyer intervention. So I think from our point of view, this was a very successful project because because we were showing the new structure, but because it was spaced off the existing, it didn't interfere with the flow of how the existing industrial building felt and stood. It's very clear what's old and new, and so we think this was a good job from a strengthening point of view. So now continue on the masonry theme. Two very big buildings built in the same decade, but actually from an engineering point of view, very different. So the Old Public Trust is an unreinforced masonry building. It's got some small bits of steel cast into the facade, but the main steel in the building is holding up the floors. It's quite a narrow building. It was designed just to be offices, so natural ventilation, no more than 10 metres between windows. The rules of architecture of this time, that because we didn't have air conditioning and building services and that sort of thing, so good proportions for living in it, but very difficult structurally. We've got this long, thin building with these steel beams spanning across it, sitting on unreinforced masonry. So the building was very weak. But the masonry around the perimeter was very solid. So it had this it's on good solid rock. It's got this good masonry, but it's very weak in the transverse direction. So how do we approach that? And I'll get into that in a minute. Whereas the wool store, when you understand it structurally, is actually a very different building. It's an industrial building. It was made as a wool store, obviously, but for very heavy wool bale loads. So it's a steel frame building, and even though it looks like masonry, it's actually the steel frame holds up the whole building, and then the steel frame is then clad in masonry. So it looks like a brick building, but it's actually a steel building with a masonry cladding, and that's sort of good and bad because it's built in so strongly around the steel that they tend to fight each other a bit, and that makes it a bit difficult. So what also made this project a bit difficult is the fault is literally right outside the front door. It's the scarp that comes down when you drive down out of Thornton onto the quay. So we were really, really concerned about the foundations of this building and what was going on there. And so what we tried to do with this building is embrace the steel frame, but then what we call selective weakening, which is some little delicate cuts to the masonry to let the building work like the steel frame already has the strength from. Work with the building's natural strengths, if you like, and just with some small interventions sort of free it up a bit. So I'll go into that in a bit more detail. Part of what was difficult about this building is it was built in 2 stages. You get that with the older buildings. They tend to get changed over the years, except for this, which is pretty much as it was when it was designed. But so the original 1910s building is there on the left, which is the rectangle, and then later there was a reinforced concrete addition to the south. So we started, the client was very brave. They tried to keep the building fully occupied throughout the strengthening, which was probably painful for some of you if you went to visit the shops, but and it was a little bit difficult for the tenants. But what it meant is that there was still some life in the building, and it was occupied. And reflecting on this at the end, the client said, "Look, it was great because often if you empty a building and then strengthen it, there's this kind of pause afterwards when people have to work out how to reoccupy it, and it gets a whole new life, and it can kind of lose what it had before." And so what was cool about this is that by being brave and having people continue to work and shop and eat in this building right throughout, it never lost what it always was. And so the use that it was before it started was the same when we finished. So it kept some momentum, kept a little bit of rent going for the client because the stuff's expensive. And so tricky, difficult, but expensive. So we had to brace the south end a bit. We call these floor diaphragms, so it's really the floors of the building. What we want to do is collect the loads from all the walls and tie them in together. So the old floors are just boards on joists, and so we added bracing to the floors to help tie everything together. And the addition had a concrete basement. In the original part, it just had very large caisson mass concrete probably shoveled in by hand footings. And so we're really worried about how these would respond when the ground's all moving, with the fault moving and earthquakes and that sort of thing. So what we did is we dug out the whole basement, we cast a big raft to join everything together, and then we piled and anchored the existing foundations down. So we created new rigid connections through the beach and into the alluvium underneath the old beach that the building was built on. We had some bracing inside the building because the facades, the masonry in the facades wasn't strong enough, but we put the bracing inside the building where you don't see it on the elevations. So you can see it, there's some K-frames within the building, but you walk under them when you're inside, but the idea was that they were of the same sort of ilk as the existing steel frame. And then in the other direction, we had very stiff boundary walls. And what was interesting about these is they were almost strong enough for the 70% of code that we were strengthening this building to. But what we were worried about is because they were so rigid that they would damage the foundations because they're so strong that anything that the ground moves causes them to push and pull on the ground each side and potentially cause liquefaction. So what we ended up doing is we ended up slicing these walls into 6 pieces, and so that each piece could move, and so it was more flexible. So this is that selective weakening I'm talking about. So as engineers, we like to control things, so that was our way of getting control back off the building. So we're slicing the building into pieces, and then we're connecting it up with a new piece of steel that we can measure, and so we know how strong that connection is. So now we know what the performance of the building, because we've done something ourselves and we've kind of taken control of it. And because it was built in 2 stages, we had to try and join these up. The grids didn't line up, and it was all a bit of a mess. So we had these very complicated bits of steel that had to try and hold one building to the next, and at least the floor levels line up, which doesn't always happen with these buildings, and kind of connect it through these panels of the building that were moving in earthquakes. So some really kind of complicated bits of steel, as you can see, to make that happen. So you get this crazy bit of structural modelling that you're trying to predict how the building works. But what it really came down to for us was, let's get a couple of good details that run around the whole building and get a bit of a theme going. So bracing up the floors, what we tried to do is pick up the kind of the language of the sort of Victorian detailing of the old steel frame, but it was different because it was new. So we didn't try and use old rivets or anything like that. So we used new bolts, but we used the kind of lots of stiffeners and really engineer-driven details, which is, you see in the old railway stations and that sort of thing. So we tried to express this in the same way, where instead of just using a bigger bit of plate, we used more smaller bits of plate to try and show how the engineering was happening, and therefore kind of make them more in keeping with the existing building. And we've had some comments from people looking around and say it's quite in keeping, and I think that's important, that you don't try and mimic exactly what was in the old building, but you do something of the same vibe, the same theme as the original. Something that always happens in these jobs. This is the blunt end of structural strengthening: digging in under buildings, horrible, hot, wet work, digging around trying to strengthen these foundations. I don't think people quite appreciate the work that's done by some of the contractors to get in and under these buildings to try and make this happen. It's noisy work. It's difficult, but it's essential, and it's often the place where we do the most work to kind of make sure everything's tied together. And there's lots of metaphors throughout history and religion about having a good foundation. So important part of the job. Testing the anchors, testing the new connections we made through the beach into the old into the alluvium underneath. Connecting everything up, lots of reinforcing, connecting to the steel frame, both new and old, above. Trying to put braces up in a live building. This is the sort of thing that people are doing. Like, people were shopping next door and eating in the cafe, and so people are trying to, the workers are trying to lift this 1.5 tonne brace up into place right next door. So I think it's fun. It's not always fun for the people on site, but this is the kind of stuff you're dealing with, and it's so very different from building new buildings where you've got a crane. It's all about building it quickly. It's more craftsperson like. You're trying to. That's why it's expensive, unfortunately. But you're trying to match something and mate it up to the existing. And an old building's always got different measurements, and it's always moved a bit. So it's difficult. And one of the achievements was keeping some of you might have met the cafe owner in the wool store, and she's a very strong personality, and keeping her happy throughout the project was an important project goal. So we think we've done, for the wall store, you can see here there's new bracing, but you're seeing the old behind it. Again, it's a little bit like Shed 13. So you're seeing old and new, but the new has some ilk of the original design in it. So that's our way of trying to make it not fight it when you walk around the building. So in contrast, the old public trust, so we've got this, instead of a steel frame, we've got this masonry frame, but you can see in the photo on the left, those are the girders that hold up the floor. Now, we had a summer student from the architecture school work for us, and she did some research into the history of this building. And what she came up with was that after the earthquakes that Wellington felt, including 42, there were quite a few, between when the building was built in 1912 and 1942. And what was happening is they thought beams were falling off the building when it was shaken by these earthquakes. And what was happening is these old girders had plaster around them, and the floors that were just cast on each side, as they moved, they were making bits of plaster drop down. So people thought the beams were falling on their heads. That's what was reported in the paper, but it was actually the connection of the floors, each side of the beams, was the problem with this. And what was happening is this very long building was kind of moving like bananaing in the middle in these earthquakes and breaking all the plaster. So that was a big challenge for us to fix. In 1983, they realised that the building was not strong, and so they did what was then seen to be the right ways of doing seismic strengthening. So they did what we did in Shed 13. They cored down through some of these big pediments, and they pre-stressed them down, so they did some really good job of clamping that together. And they cast some shear walls where I put the bubbles on there, around there, to try and brace the building more. So that was to try and brace the building along and across. So they, what we did in the 80s and 90s, and it's even gone on for some other engineers, is to kind of, rather than work with the existing building, it's like, well, to do my engineering calcs, I can put a new building inside it, and then I'll connect the old building to it. And that was often a way that was done in engineering circles, and it's really, it's not seen as good practice now. What we try and do is understand the existing building. And what we did by studying this facade, and we used this as part of, in 2014, we issued new guidelines to the New Zealand engineers of how to strengthen masonry buildings and how to do all the calculations, and we drew on the research that had been done in North America and Italy especially, and to try and sort of improve, especially after Christchurch, how us engineers were actually, how is the masonry naturally strong? And what we found with Old Public Trust is the piers and the spandrels of these long facades, the main facades that run along Stout Street, back and front, is that they could almost take the full code loadings, because the piers would rock and then they would come back on themselves, and there was no diagonal cracking. They were very predictable movements in the facade, and so we had this great building that had a lot of strength longitudinally, which didn't really need the shear walls that were added in the 80s, but it still had this problem across the building. We, on these facades, some of the piers are really big, and so we did some discrete cuts to make the big pier two smaller piers so that all the piers were even, so that the building all moved in a more uniform way. And we were pretty delicate at that, and you can't even see them from the outside, these extra cuts. They're within the masonry. And then when they redid the mortar joints, we dig out the mortar and we put stainless steel rods in there, so that helps reinforce it so that there's no sliding off of the piers on those joints. So again, really using the strength that's already there. Foundations, we've talked about this before, so try and anchor the building down to the good rock that was underneath this. And then across the building, we decided, well, we just needed to do something really, really strong, but doing things that are just strong in an earthquake isn't good enough, because we never know. Every earthquake surprises us. When we have a new earthquake, us engineers learn something. So if you pick a level of strength, the next earthquake could always be stronger. So what we try and do is absorb the earthquake energy, like I said on Shed 13. So we call this ductility. So what we did, instead of just making one big rigid shear wall with doorways in it, we made a slot in the shear wall. And this is where you walk through out of the main entrance into the floor plates you can see there in the photo. And that's coupled up by steel beams. So instead of the shear walls being all rigid, what they can do is move, and the steel beam gets bent by the earthquake. And the steel is very ductile. It can go backwards and forwards in the earthquake and use up the earthquake energy. So again, reaching out, trying to get some control over how the building's going to work again. but it's still very stiff because you've got these massive walls that are talking to each other through the steel beams. And so once we put these walls in to brace it, we still had the problem of the building wanting to snap in half, and I drew these diagrams internally, on the ones on the left, after the Seddon earthquake in 2013. The building had started to crack on these same lines that we'd seen from the previous earthquakes, and we were really concerned that the building was going to had been damaged and was getting worse, and so we put some monitoring in the building, and then when there were the subsequent earthquakes, we monitored how the building moved and checked that it wasn't getting worse, that it wasn't moving more and more each time where it would get up more momentum and destroy itself. So I didn't publish these sketches to the client, who was quite nervous about the building at the time, but the big problem was that the building was twisting around and tearing at its floors. So we had these old steel beams that were in the floors and that we could see at the top, and they were underneath a raised wooden floor. Now, Maurice Clark owns this building, and he was doing the strengthening, and he and I had many discussions about what we should do about these floors, because there were some really nice old floorboards within the building, and that sat over the top of this concrete floor in the steel beams, and Maurice was very much like, well, we've got to put the wooden floor back, and I said, yeah, but the problem with that is we need to put all this bracing in, so where do we put it? Do we put it underneath where you're going to see it if you look up? Could we pull up the wooden floor and put it down and then put the wooden floor back? But then once we investigated the building, we found that in the 80s, when it had been refit, it was only about 5% of the wooden floor left. Most of it had been taken up, reused somewhere else, and there was particle board everywhere. So that shortened the argument quite a lot. So we basically pulled up all the wooden floors, and we used that thickness of the old wooden floor to recast concrete. Now, we normally don't put that much concrete in an old building because we're making it heavier, we're making it worse, but we'd done our studies in the long direction, we knew we had extra strength in that direction. And what it also would do would make the old steel beams sag. So what we did is we propped those beams up, and we put things like bolts that are welded to the steel beams. And when we recast the concrete and then deprop the beams would act with the concrete together. So we made the beams stronger by making this connection to the new floor diaphragm that we'd put in. So by these new strips of concrete, we were able to connect our shear walls and tie everything in very well. And on the outside, to make this concrete stiff enough, we also used some cables, some post-tensioning again, because we want to stop the concrete from cracking, because cracked concrete can be like 4 times as flexible as uncracked concrete. So we wanted to squeeze it up and keep it stiff so that it worked with the old masonry. We did further strengthening to the parapets because under the new codes, the loads were higher than they used in the 80s, connected in all the really difficult parts around these mansard roofs and stuff, and we see really often these with the heritage buildings, it's the little bits that are the tricky bits, and they take these sort of sketches that we do. Some of my staff who really love doing this kind of work, they end up with dozens of these sketches at the end, trying to communicate to the contractor how to fit something in there, and it's contrasts so differently from when you draw something new, and now you can just model it in 3D and draw up all your joints in full 3D. It doesn't really work with an existing building because you don't know where things are until you actually open it up, and it can be like 3/4 of the way through the construction project before you can even see what you're really dealing with, and so you've got to react very quickly and then try and keep knitting it all together. Right, so going from masonry to something a bit lighter. Oldson Pools, we got involved, Wyn Clark, who's done the assessment on this building, very engineer, very passionate about heritage, had done some assessment on Oldson Pools, and this is one of his models from his report that he'd finished just at the end of 2016, just when the Kaikoura earthquake happened. And he was saying, like, the buildings naturally has a lot of strength, but part of the thing with the old timber details is that they were mostly mortise and tenon, and so they were notched in, and so the building was potentially very strong, but what would happen is these tongues that were slotted into the wood would withdraw in the earthquakes, and so that loosening was possibly compromising the strength, so the building had an ability to be strengthened to 90% of code with the structure that was there, but all the connections weren't up to that, and so he needed an engineer to go through and work out how to strengthen all these connections, and so that was the job we took up. But then Kaikoura happened, and those of you who went into the church after the earthquake, you might have noticed a whole lot of truck stops around holding the building together. We went in December. That's me measuring the plumb of the building. The building got 150 millimetres wider after Kaikoura. It shook down and expanded, all these joints pulled out, and the walls, so some of the walls are on almost 100 millimetre lean. So we were there was a bit of a oh shit moment at that point. I was actually supposed to be off on holiday with my family, and I ended up staying another 2 days to do this stropping design, and then I flew up and joined them later for I think it was Christmas that time. So what we did is we bound it together with straps, and so that's why the building, by keeping these joints shut, the building still had all the strength. But then the job was, well, how to do that in a permanent fashion. So what's tricky about Oldson Pools is it's a mashup of all sorts of different bits and eras and adding. It's been pulled apart, it's been reconnected, it's nothing is the same anywhere in it. So and then it had a really heavy restoration by the Ministry of Works in the very early 70s. So we found these great drawings in the archives. So they told us quite a lot about the story of what they tried to do in the 60s, and really it was restoration but not strengthening. So they were trying to put back all the braces that were there. It was very much assuming that all because there's quite a few diagonals in the building, they were assuming that they were all good enough, and there were these great drawings where they're notching away dimensioning how they have to notch the end of each brace and kind of fit it in and do all the sort of stuff that you have to do with these wooden buildings to fit them together. And then what became slightly the bane of our life were the transepts of the building, where they had these timber frames where they'd put different braces in, but because they were such an amalgamation of different years in it, nothing really lined up. So they kind of the sort of northwestern wall that at the end of the transept that faces the Tinakori Hill, that had been moving around quite a lot. So they almost rebuilt that, but they rebuilt it in the old form, and they just added a couple of diagonal braces to stop it moving around. And that was actually the worst thing for us there, because what we're trying to do when we strengthen this building is to hold the joints shut but not stiffen the building up, because what keeps this building being strong is the fact that it can be flexible. It's timber, it can move, and all the joints squeak, and that squeaking of timber sounds facetious, but that's using up the earthquake energy. We just got to have that little bit of give, all that little friction spread out through the building. That's what makes it strong. So we've got to not make it worse by over stiffening the building. So that's quite a challenge for us, because you're talking about how old materials work, and the calculations are plus or minus 2 or 3 times, not the kind of 10% accuracy we're used to, and so you've got to kind of get your head around that. So the concept was that we had the main frames across the building was to tie those. There was a lot of discussion with Russell Murray, who was the heritage architect on this. We had the truck stop ties across while it was being used after Kaikoura, and there was a question, could they be removed again, and so that when you looked down, there wasn't any new structure across there. And we looked at it, and it's like, no, this building will always get wider when it shakes if we don't have that ability to tie it. So we just picked 3 lines where we would put a tie across the building, and then we went in behind all the clerestory windows, and we tied along the building. Basically, the building is all basically just tied together everywhere, and then pinned gently at the joints, not too heavy, not too light at the joints to allow this movement. The transepts were the tricky part, the green bits in the sketch and plan. So they act as, traditionally, and from physics, they act as buttresses to the building, and so they were attracting the load to this kind of strange bracing, which I'll go into in a little bit later. So the concepts were, in the old timber, we didn't want to tighten it too much, so we put blocks in that were let into the wood, and we put clamps in, but they weren't too tight, and so we're notching and we're pinning and we're using screws. Now, these aren't the screws that you're normally used to that are about this long. These are screws that are this long, and they're up to 10 millimetres diameter, and they're made in Germany or Austria, and they're very high tech. They cost about 100 times what the little screw does, but these are the new tools that we have And by looking at where the thread is on the screw, having sometimes gaps in the thread, and looking how much you squeeze the joint before you put the screw in, that's where we can start to get this control over letting the joints be flexible but strong. And so what we're trying to do is do this kind of, you can see the sort of blocks that were hidden in behind and then bolted, then clamped through, so that you're trying to think of the builder trying to reach in and fit it, and you're also trying to think of, when you're looking up at it, how is it going to look visually. Continuing my foundations theme, this is a bit more like people are used to under their houses. We had to go and brace the subfloor, so it's like same as you see braces under your timber houses, except that they're about 2 or 3 times as big, and so we went through and did that everywhere. Bit difficult because there was a whole lot of asbestos lagging from previous services there, so that all had to be cleaned out before we could even go under there to inspect it all. We put new foundations under the transept so that the transept, what we decided is we would make the wood move a bit, but if the wood ever got overloaded, we put in a foundation beam that was only just heavy enough so that if the earthquake was bigger than we expected, the building would lift the foundation beam. So therefore we're getting that control back, so that instead of the wood upstairs breaking, it would always lift the beam. So, so there's a little bit of control for us there, that in case the shaking was ever bigger than we predicted. So created these sort of pads underneath the footings and a beam that sat on top so that it could rock around. And then with the braces, we're running rods. You might have gone and looked at these up close in the last couple of years, so we ran rods in parallel to the timbers, but we ran it about halfway across the wood. So when you see it, when you look at the timber, you're still seeing the edges of it, but there's a rod sitting there just off it. And so those rods are only there finger tight. Some of them have epoxy fixings, some of them have fancy screw fixings at the end, but they can stretch a little bit. So again, letting the joints open and have a bit of give to the steel. So the building still tries to move how it always did, but then is caught by this reinforcement we've added. And then a lot of these panels were then taken off on site, and nothing ever lined up. It was worse than we thought, and poor old Matt from our office, changing details, reworking out how we could route stuff up, putting wedges in to line things up, and Tim from Maycroft, who sadly passed away about a year after this was finished. These guys were so into the carpentry. They had young apprentices who were learning this stuff, and once they got the bug of working on this building, you had to think 3 times and then only put 1 screw in instead of just working hard. Once they got the bug of that, they were loving it, because beautiful old timbers, all beautifully seasoned, and the vibe and the motivation amongst the workforce was really great, and it made it a good project. So this is what we ended up with at the end. So you're seeing the rods, you're seeing the timber, you're seeing it, you're not hiding it, but we felt that this would give the most resilience for the least visual impact, and complicated little blocks with fixings and ties around that. It's quite interesting. We could see one of the columns had quite a kink to it, and behind where the clear story panels were, there's a whole lot of decorative panels just below the windows. So we suspected one of the columns was already broken, and we come up with a detail to sort of splint it. And then when we took the panels off, we found another column on the other side had broken too. So we think both of these columns broke in kaikoura with the movement. So when the building had been moved, more chiselling out and notching of the beams had happened at the clear story, and so the timber was weakened. So these columns were actually snapped in kaikoura. So the damage was worse than we thought, but luckily we'd sort of stropped the building together in the interim. So these are the final details. It takes a lot of drafting, to get everything lining up, the blocks, everything at right angles, blocks of steel with threaded rods, like your kind of old Victorian kind of machinist kind of stuff. You get back to that sort of thing to get these details working. I really like that sort of thing. You've got to kind of get the bug to get these working. And so we think that in the end, all you're seeing is a few rods flying across the space. And my partner's actually a photographer, used to photograph in the church quite a bit. And so the idea is that you can still get the kind of shot that everybody takes in a wedding, and you only just lightly see two high tensile steel rods flying in above your head in the most important position, and there's another one back behind you above the entranceway. So, and then over in the west aisle, we've got another extra tie along there, because that had become a bit loose in the earthquake again. The bell tower was tricky. Tall, slender, wants to rock. So what we did is we said, okay, rather than trying to brace it, we said, okay, let's just tie it all together and let it rock. So we put a foundation down that was heavy enough to absorb enough earthquake energy, and then what we did is we tied all the feet of all these braces together with this, you can see the frame that we mocked up next to it, so this ring frame that is just underneath your feet when you walk into, and that grabs hold of all the braces and connects it to the foundation. So the tower still rocks like it used to, and that absorbs a bit of earthquake energy. So we're following all the old lines of how the building naturally worked, and then just augmenting it where the forces all concentrate, and therefore we've got to use new screws, high tensile steel and stuff to do a lot of work in a very small place. So I thought that segued quite nicely into this building because I'd never seen the drawings from this building until Nick sent them to me. And I got really excited when I saw them because blocks, pins through, tie rods, this was done in this building, in 1970, 71. Like, the detail here is amazing. Like, it's clamping all this wood together, and just by gently holding it in place, it just can't displace structurally. What you probably can't see very well is right up near the top, there's some square cutouts in the wood, and there's some bits of steel that are fed through. You can see it in behind here. And so this is the stuff we were doing in Oldson Pools, and this is what we're doing in buildings like Nelson Airport, where we're using these high tensile modern wood technologies. And this was being done, almost 50 years ago by a master. So it's really cool. So I find that particularly exciting. And the drawings that show, they look like the sketches my engineers have to do to pull these buildings off. They're hand sketches. They're more views than you'd normally expect to really be able to describe the shape of them. So what I thought I'd talk about today was, so when Clark's done an assessment of this building, it doesn't need strengthening, but I'd say, well, what if it did? What are the strengths and weaknesses of this? So what would we do as a group if we had to strengthen this building? So that's kind of what I wanted to talk about. Now, the building, green's good, right? So the building has strong corners, like these are reinforced concrete walls. And this post is great because it holds the whole weight of the building. You could almost, and we saw this in Christchurch, you could almost pull all these walls out and the roof would still stay there. And we saw that in some of the masonry, especially stone masonry buildings in Christchurch, where the roof would be left flying out there even if the masonry collapsed. So you've got this naturally strong roof form with really good details in it. But what's tricky with this building is you've got very slender members, and it's coming up the top of this very heavy wall, and so you've got this light thing that wants to move around a lot, and you've got these heavy walls that want to move around at the top there. So all of the tension in this building in an earthquake is at that line where the top of the walls are and the roof meets. And so that's and then just to make it a bit more complicated, where there's these large walls, they're all reinforced concrete. But some of the walls on the outside are concrete block masonry, and so those, it's quite common, and usually it's filled up with grout, but in this, with the age of this building, only very occasional cells within the concrete masonry are filled, and so this we've seen in Christchurch, this is a very brittle material. They're hollow bits of concrete, and as soon as they crack, they tend to fall apart. And so it's really important for this building that the strong bits of concrete look after the unfilled concrete masonry, so that it's not damaged, so it doesn't move too much. So, oops. And what I thought was really cool was that when you look at a lot of the damage in Christchurch and Kaikoura to church structures, these large walls, often in the traditional buildings, they have rose windows and that sort of thing in there. Those are always the weakest part. So when you put the windows in, you're weakening the most loaded part of the building, but what John Scott did here is there's on the outside of this wall is a cross, and so he's put the strong piece of structure there on the back of the wall, and it's stiffening this whole panel and joining it to the sides. It's interesting because this was done at the same time as the Nelson Cathedral, and so the 60s addition to the Nelson Cathedral is actually weaker than the original part because of the same problem, but obviously one architect at the time nailed it and one of them didn't. So what would we do nowadays? So the timber, I think we can just bring our new timber technologies to bear. So we can use these fancy screws. Where there might be splitting, because timber likes to split along the grain, we can actually just pin that very carefully together, and that can provide quite a lot more, a huge amount more resilience. So it's like we use reinforcement in concrete, we can now use these very technical screws to reinforce wood, so that it doesn't just have strength in one direction along the grain, it has strength across the grain. So, and this is very easy to do because you with a screw you hardly see it. So you can pin the building together and there's no sign that you've been there. So that's the hide it part. But with the unfilled masonry, well, the first engineering thing that I'd react to goes, well, we've got this problem with the hollow masonry, can we just fill it? Can we fill it full of grout? But then we're going, well, we're changing the nature of the building. It's probably making it even more thermally conductive to the outside. We might make ourselves a moisture problem, have efflorescence, all that sort of thing. So maybe we're disrupting how the building was too much by doing that. So really what we've got to do is we've got to connect, we've got to make sure those other bits of masonry are joined back to the concrete walls that support them. So I think that if we were going to intervene in this building, it would be on the outside, holding the outer roof to the inner roof, and so that could be done pretty subtly because it's not really affected in this main view that we're looking at here. But what would be tricky is where these walls are, so we've got a corner that's naturally strong, but we've got this little buttress here, so this wall can want to move around quite a bit. So there's lots of ways you could approach that. We could do what we did at Shed 13, we could put a new buttress on the inside and have it separate, or we could put a new buttress on the outside. But then are we disrupting the flow of the building, the sort of nice minimal lines of it? So unfortunately, these buttresses don't have huge foundations underneath them. So the first thing we'd want to do is come and make a foundation. Now, obviously, the floor in this building is beautiful, but we can go outside. And so it's about looking for places to do it. So I think what I would do in this building would be to strengthen the foundation pads, and then I'd probably try and clamp those buttresses down a bit more so that they were stiffer and they didn't move so much at the top. Then, really important, we want to connect, make sure that the timber and the masonry stay connected in the earthquake. Now, traditionally with those commercial buildings I showed you, we were spending a lot of time joining the floors onto the walls and making sure the walls weren't falling out. Now, with churches, an engineer's instinct in doing that isn't necessarily the right thing, because a church sits on the ground and then reaches up and connect, trying to brace the tops of these walls and take all the loads up into this roof and then bring them down again. The loads have got to go a long way, and you have to strengthen all of these wood panellings, all the sarking. We have to connect it. Hugh Tennant, an architect I work with quite a bit, was working on another of these ancient projects, and they were talking about doing the roof diaphragm and putting extra plywood on it. And I gave the analogy, it's like trying to grab a building like this by the hair and kind of try and hold it together. It's not right. So what you've got to do is appreciate where the strength of this building is, which is just its connection to the ground. So you've got to connect it to the ground and then reach up and then just try and pin the tops of the wall so that they don't become dislodged, but we're not trying to brace them. So we've got to let the wood move at the top with the concrete walls and not become dislodged, if that makes sense. Yeah, so last slide. So I guess as an engineer, I spent, what did I work out the other day? It was like 5 or 6 lectures total in my architectural training at university. It's not, design is not taught at our engineering schools. So us engineers as a profession are trying to wrestle on how to do these good seismic strengthening. Now we get a lot of help from our architects, but the architects they're not taught the engineering that goes in with strengthening these buildings. So we're all trying to discover this a bit more and trying to do a better job. So what we think is the right sort of starting point is that you start off making sure you deeply understand the existing building. You're not trying to put another building into the old building. What you're doing is trying to deeply understand the old building and only fix it where it needs fixing, and don't and no more. So you've got to be inspired by the existing, but then you've got to. The tricky bit is you're then moderated by the site constraints, like, so I wanted to put foundations down here, but we can't because the floor is amazing. So, and then you've got to be able to think of the builders working in there, like, can they get in under to do the foundations? Can they reach in to get these screws in? And the number of different, doing Oldson Pools, the number of sketches we did with drills and angles and stuff to try and work out that our details work were extensive. It's a partnership, I think. For strengthening, it's really hard, it's expensive. I think they're really successful buildings. Most good strengthened heritage buildings, people love afterwards, even more. But it's very much a partnership between the client, the designers, and the construction team, and that's all got to be really integrated. Everybody's got to be on their side against the building, because the building will have so many troubles for you as you go through to strengthen it, not fighting each other. So yeah, it's really tricky. And then, as I said, we'd spend, normally on a new building, we'd spend about 20% of our time just checking that it's all built on site, right? For a new commercial building, maybe 25%. Whereas an existing building, like Oldson Pools or St John's in the City or something like that, we'd spend 40% at least of our time on site trying to work through how to build it. So you've got to make sure that you've got your head around that and you allow for all that, and give the construction team the time and the support to enjoy what they're doing, get motivated about what they're doing, and work through the details with them. So yeah, quite different from new design. And that's it. Take questions?
Thanks, Alistair. It's incredibly informative and passionate presentation you gave. And to have that bonus issue at the end of an assessment of the chapel, if we wanted to consider, and I think there's another trustee or two in the audience who's probably thinking, well, maybe when we do the roof replacement, we should look at something that we can do at the same time.
Just a few screws, maybe it's good.
Yeah, if it's just a few thousand screws, it'll be right. So really, really appreciate that. But I do have a question, and we've had a number of structural engineers visit this building from time to time, just out of interest. And I remember one in particular was an American who, not only was he a structural engineer, but he ended up being an eye surgeon, so I don't know how that works. But he was sitting over here, and he was looking at the structure that you pointed out, the sort of nesting of rafters coming down from the roof. And he pointed at that, and he said, that's a 0 point. Because the brothers, when they built this building, the first thing they had to put in to build the roof was this poe, and it's 12.5 metres. It's a single stick of Oregon, and then they constructed the roof off that. What this engineer was saying is now all those rafters are coming together, forming a 0 moment, so you could take out the bottom bit of the post. Is he right?
He's right, but then you'd have to be He's right, but you'd have to be completely reliant on all the rest of the walls being intact and exactly where they started. So that's that little bit of redundancy that this building has, which means that, it's not just reliant on one thing. It's got this extra post. And, I think John Scott's a Māori architect. The poe in the middle is very important and poignant in New Zealand traditional architecture. So I think that should be there for lots of reasons.
Well, and I agree with you, and because this is a heritage building, Category 1, and also it's protected under the Wellington City Council's district plan with the interior protected as well as the exterior. We're not allowed to make any changes. So, Roger, will cancel that agenda item at the next meeting. Yeah. Does anyone have a question for Alistair? We have a little bit of time. I'll bring you the microphone if you do.
We were told this afternoon that this building is 78 to 80% of new building standard. Is that because it has degraded since it was built, or was it never up to the modern criterion?
Good question. So earthquake engineering has evolved a lot in the last 60 years in New Zealand. When I first started in the early 90s, the traditional codes designed most buildings for 10% of gravity was the bracing that you needed it, and if it was a government building, it was 12% of gravity. That was what was the 1965 code. The kind of forces on the building that you design for now, if you don't absorb earthquake energy, is almost 10 times that. It's almost 1 G, so it's almost picking up the building and turning it on its side. That's 100% of code. So that's the level of change we've had in the last 50, 60 years in earthquake engineering. because it's very hard to make a building that strong, what we do is we absorb, we can quarter those loads by putting in this energy absorption, and so therefore we can design a building for 0.1, 0.2 G, and then make it work really hard to absorb earthquake energy. So it does that, it does the same job, but through cycling and absorbing that energy, if that makes sense, rather than just strength. So there's been a lot of change, and I guess what the public's been telling us is there's been, and the building owners especially, has been a huge amount of change since Christchurch. So there's a lot that we've learned as engineers that we used to take as gospel that was proven wrong in Christchurch, and we've had to change that. We've issued new masonry guidelines in 2014, new older building guidelines in 2017, and even now they're looking at what the actual earthquake hazard is and whether that should change again. So it's a really difficult time. We've spent a lot on these buildings, so there's a kind of philosophical thing of how strong the buildings should be, how much resilience we want, and sometimes for these heritage buildings, I don't think we should just pick a number. It's an older building, it's a bit like an old car, there's only so fast it can go. So you want to find that point and make it go as well as that and no more. And so that's part of the art of the strengthening is understanding that point and not trying too hard, because then we clutter it up with all the structure. It costs a lot of money and it kind of ruins the natural heritage of the building. That's probably too big an answer for your question.
Thank you. Very interesting, and I agree with Nick, your whole passion comes across, which is wonderful. What I wanted to ask is, if you think about the age of buildings, say we'll take Wellington for example, and those that fared reasonably well after the 2016 quake, why have the new things fallen down, basically? Why did Defence House have to go, which was only about 8 years old, and the BNZ on the waterfront? I imagine that was partly liquefaction or partly the weakness of being on the waterfront. But it seems, with all the cumulative knowledge, why were those buildings not able to basically survive?
There are three parts to the answer to that question. So it's very complicated, so I'll try and make it three simple bits. One is that the shaking in Wellington was quite unusual, and we discovered what had been mostly known in textbook and was mostly overseas done in research, this thing called a basin edge effect. So what that means is, as the waves came up from the south, we were at a big distance, so there were no small waves, there were just the big, long, slow rollers, and that's what it felt like. What happened is that they concentrated, they bounced sort of approximate, the geophysics is a lot more complicated than this, but they sort of bounced into Thornton, they bounced back up, and then they bounced in again. So like the water at the edge of a wharf, you got these waves coming in and interfering with each other, so they doubled and tripled in size. So that's why Centreport, and then there was another little phenomenon of that around Te Papa. Just there was extra shaking there that was 3 or 4 times that in other places, and then on rock, there was almost no shaking because it was long and slow, so there wasn't the stiff shaking that would normally damage buildings like this or the old masonry buildings. So any building that moved in a long and slow way, it was only those buildings that moved in a long and slow way that got shaken. The other thing that we started doing in the 70s is making buildings out of bits. We used to put lots of reinforcing in and pour concrete in and join it all up, and then we started making buildings off-site in little components, and we weren't very good at joining them together. And we've learnt that, and it's taken us 40 years to really learn that. One of the flooring products is particularly vulnerable, and we didn't realise how vulnerable, and that was in the BNZ. So even though some of these buildings didn't break, we never used to design buildings to worry about damage as long as it didn't kill people. So that was the idea, where people would go out, and the thought was that people would demolish these buildings. But what we had in Wellington in 2016 was the learnings from Christchurch, which is, it's terrible because all these buildings get knocked down and they're not easily replaced. It costs a lot of money. It's all the disruption to the city. It's wrong. And so we had these buildings that were designed to be disposable as such. They weren't designed to be preserved. And so that's why I sort of talked about with some of our projects, connecting things with bits of steel and things that can absorb earthquake energy that can be taken out and put back in. We call this low damage design. So it's not trying to be base isolate building. It's not trying to do the Rolls-Royce way of doing it. It's trying to make the buildings more repairable. And so that's a learning that's really only come in the last 15 years in international circles as well, outside base isolation, which you probably know about. So.
I wonder if you could comment on the Christchurch cardboard cathedral. Must be very different for an engineer, that sort of thing.
Yes, I know a little about that cardboard cathedral. Site engineer's sleight of hand. We weren't involved with it, but the architect's done a lot of cardboard buildings. A good friend of mine that I work with in the UK did a couple of his buildings, Shigeru Band's buildings in the UK, and in those he's very keen on using cardboard structurally. Now, cardboard's a nightmare structurally because when you load it, it shrinks and it keeps on shrinking for the life of the building. It's like a log house or whatever like that. So it's really tricky. And Helen did a whole lot of testing at Imperial College for the building that she did in the Millennium Dome. But in Christchurch, they cheated. So because they didn't have the time and they couldn't necessarily get all the products. So it's actually a wooden roof that's clad in cardboard. So it's called a cardboard cathedral, but the kind of the cheeky thing is it's actually a timber roof that's got cardboard cladding on it, which is a little bit naughty, but yeah, it's a little bit of a shame in my view because we know how to do it in cardboard. But that roof would be sinking over its life, which maybe it doesn't matter if it's temporary, but Christchurch seems to think that it's permanent now. So.
Well, thank you again, Alistair. Don't go away. Got a few people to thank, and first I want to thank those people who've made donations online and here today using the Koha box. It certainly helps, like the Po here, support the trust. The sponsors, LT McGuinness for the events that we've enjoyed yesterday and today. The Sound and Vision crew, we've got Tony, Chris and Alec here on Sound and Vision. And also there's a chap hiding in the back there behind the screen, Rob Sarkis, for the very first time, he's enabled the Trust to do a live stream event. So it's been a bit of an experiment and we'll be interested in hearing the feedback. So big thank you to you, Rob. Also Tina and Kathy, Sally and Sarah at the NZAA who helped set up the live streaming registration process with Eventbrite in the Wellington branch of the NZAA, and David Batchelor from Wellington Heritage Week. I also want to acknowledge and remember Brother Joseph Kelly, the foreman, an untrained carpenter who built this chapel and led the team of 5 brothers who are also untrained carpenters. They had one power tool on this project. It was an electric drill. Everything else was done by hand, even the pouring of the concrete up here. Wheelbarrows towed up ramps with 2 men in front on ropes and 1 man behind steering the wheelbarrow. I also want to acknowledge Jim Allen, who celebrated his 99th birthday in the 22nd of July, who is artwork embedded into the fabric of this building, as we talked about earlier, and his work with the Christ figure and the Stations of the Cross. And of course, John Scott, the architect, we like to regard this as his masterwork. He's done a lot of excellent buildings and lovely houses and a number of churches, 6 in total. And I'd like to think that this one is regarded as masterwork. There's a book about the chapel which is on sale today, by the way, just a little commercial plug for $20. Give me the money, I'll give you the book. But I would like to give Alistair a book. But it's not a book about the chapel because he knows the chapel intimately now, and obviously we're going to have to sit down with it at some point when we have the funding and look at a long-term incremental structural strengthening plan. But Alistair, hopefully you may have this in the library, I'm not sure, but in 2014 the late Ron Sang gifted a large number of books that he had published to the Trust, and we sold a lot of them, but I found one in my studio at home, and on behalf of the Trust I'd like to present this book on Hautiri.
That's amazing.
And it's still in its original plastic wrapping. So Alistair,
thank you so much. Really
appreciate it. In memory of Ron Sang, who spoke here in the chapel about some of the large artworks that were lost in New Zealand and or stolen. We are at the beginning as a trust of forming a digital archive, and we're hoping to, within the next 6 to 12 months, to have all the events that we've recorded here at the Chapel, plus archival material. People have spoken here, been filmed. We've had the Futuna lecture series, and that next year that'll be live streamed from here, so we have more of a national reach and ultimately a global reach. So you're a part of the Futuna history now. You're part of the congregation. We won't pass around the collection plate, but I've talked about the koha box. When you leave the chapel and you're quite happy, we're happy for you to remain and have a look around, just be mindful of the roadway out there. It's a 20k limit, so it's a little bit quick. So once again, thank you for coming and participating in this. Thank you for the online people if you're still with us, and please be safe. Thank you.